Bismillahirrahmanirrahim. This is the second lecture of our subject Automotive Technology, and today's topic chapter we will cover the manual transmission or the conventional transmission. Now, the basic slides which I showed in last lecture also, the powertrain or power flow of a conventional rear wheel driven vehicle. Engine from where the power is developed. It is then transmitted to the flywheel. From flywheel, it goes to the clutch. And from clutch, it goes to the gearbox or the transmission. And from that transmission, it is transferred to the propeller shaft, then to the differential box or differential gear, and then distributed to rear, right, and left wheels. And these are the allied topics which we will study. So this is the basic power flow of conventional rear wheel driven vehicle. Now, today's topic is conventional transmission or the manual transmission. What is transmission? A transmission, also called a gearbox, is a mechanical device which uses gears to change the speed or direction of rotation in a mechanical device. A transmission, also called a gearbox, is a mechanical device which uses gears to change the speed or direction of rotation in a mechanical device. Many transmissions have multiple gear ratios, but there are also transmissions that uses a single fixed gear ratio. So there are, may it have a single fixed ratio, or it may be transmission having a 3 forward gear, 1, 2, 3, and 1 reverse gear, or 4 forward, 1 reverse, or 5 forward, or 1 reverse, and so on. Depends. So this is a link to video animation. You can watch it in your own times. Now, power flow or powertrain for a front wheels driven vehicle. In the last lecture, I have also explained this thing. First, the engine power, then we have a transaxle assembly. Transaxle is basically a major assembly which consists of 3 sub-assemblies. First is the clutch assembly, which includes the flywheel and the clutch. Then we have a gearbox, the transmission, the second sub-assemblies, and third is the differential. And there is no propeller shaft in the front wheel driven vehicle which are having a transaxle. So only difference is of propeller shaft which is absent here. We have differential here, and in some book it is called as final drive, or in some book it is called as differential here. Then it is distributed to front, right, and left wheel. So the powertrain or power flow in a front wheel driven vehicle, we have the engine where the power is developed. See the color coding of the same color coding was used in the previous chapter, same slide. Transaxle then to the distributed to the front, right, and left wheel. And then transaxle is a combination of 3 sub-assemblies in which we have a clutch assembly, gearbox, and differential. Now, what is the difference between a transmission and a transaxle? I have briefly explained. A transmission is used on rear wheel drive vehicles, whereas a transaxle is usually used on a front wheel driven vehicles. A vehicle equipped with a transmission uses a separate differential to split the torque equally to the drive wheels. A transaxle includes a differential assembly. In a transaxle, the differential, sometimes called the final drive unit. So there is a differential, and sometimes we call it a differential, and sometimes we call it a final drive unit, is incorporated in the construction of the transmission. But in this transaxle, we do not have the propeller shaft. Now, let's discuss this case in which we have 5 forward gear, 1 reverse gear, and 1 neutral gear. What is neutral gear? Neutral gear is that gear in which your vehicle is stationary, engine speed is high, but the vehicle is stationary. Engine is moving at a high RPM, whatsoever the RPM you are producing with your accelerator throttle, but there is no movement or output. So vehicle is stationary. Okay. So that gear is the neutral gear. Now let's suppose the engine is moving at 1000 RPM. But in the neutral gear, the vehicle will be in stationary condition. There will be no movement. And when we shift from neutral to first gear, the vehicle speed is slow, low. But engine speed, as we have for general understanding purpose, we have fixed it or taken as 1000 RPM. Engine is rotating at a high RPM, but your vehicle is moving slow because of the gear ratio of the first gear. Then we have a second gear in which the vehicle speed increases. It is more than the first gear, but less than the engine speed. Okay, let's suppose for a understanding purpose, in first gear, let's suppose the speed is 400 RPM. Okay, as of the transmission, the gear ratio is something like engine is moving at 1000 RPM. So we are getting somewhere the ratio here. The second gear, the speed is more than the first gear, which we are using, but the engine speed decreases as the shift is made. In third gear, vehicle speed continue to increase, so it is more than the second gear. Engine speed is kept in a narrow range. Then in fourth gear, again the vehicle speed is increasing, yet engine speed is about the same as in the third gear. So in fourth gear, we are having the same rotation speed of the crankshaft and your main output shaft. So we call it as 1:1. In fifth gear, the vehicle speed is more than the engine speed. It is the condition when we have overdrive. In first gear, second gear, third gear, we have gear reduction. In fourth gear, it is a direct drive, 1:1. In fifth gear, it is overdrive. Your vehicle is moving faster than your engine speed. Now, before we go into detail of the transmission, how it works, let's talk about something regarding the gears which are there. First, just to brush your brief knowledge of your gear theory, spur gears having a straight cut teeth like this. They have a teeth profile straight. So, and second is the helical gears. The teeth of the helical gears are cut at an angle to the gear axis. So this is the gear axis center line, and this is the angle which they are making with the center line. Okay. Spur gears has the straight cut teeth as we straight cut teeth profile is like this. This design is very strong and is used where strength is important. So straight cut teeth is used where very design is very strong and used where strength is the utmost important thing. Spur gears are noisy during operation. When they rotate, they produce lot of noise, but the strength is here more. In helical cut gears, on the other hand, operate quietly but create a force in the line with the axis of the gears due to the angle of the gear teeth. As we know, they have a helical angle with the center line, so this axial thrust of a driven gear is in this direction and axial thrust of a driving gear is in this direction. But they operate with a less noise. Now, when two gears are mesh, the One is the drive gear and other is the driven gear. They both, when two external gears mesh, they rotate in opposite direction. That we are giving it here. The drive is in counterclockwise direction. The driven gear will be in clockwise direction or vice versa. In bevel gears are often used to change the direction of rotation and typically used in differential. So if this is your drive gear, we are moving. The other gear is at the 90-degree angle axis. Okay, so these types of gear are used in a differential. Power is distributed at 90-degree angle. Now another gear, a pinion gear meshed with an internal ring gear rotates in the same direction around a parallel axis of rotation. This is a ring gear, okay? And then we have a pinion gear. And this is the axis of the rotation. Pinion gear axis is like this, and ring axis is like this. So it rotates in the same direct axis of rotation. Now, a differential uses a hypoid gear set to provide a change in the direction of torque, and a gear reduction torque increases to the drive wheel. So this is your ring gear and this is your pinion gear. So hypoid gear are used in this differential assembly. Now gear ratio. When one gear turns and other, the speed that the two gears turns in relation to each other is the gear ratio. The relative moment, relative speed is the gear ratio. When one gear turns another, the speed that the two gears turns in relation to each other is the gear ratio. Gear ratio is expressed as the number of rotations the drive gear must make in order to rotate the driven gear through one revolution. Okay, so I repeat, gear ratio is expressed as the number of rotations the drive gear must make in order to rotate the driven gear through one revolution. To obtain a gear ratio, simply divide the number of teeth on the driven gear by the number of teeth on the drive gear. To obtain the gear ratio, simply we have to divide the number of teeth of the driven gear by the number of teeth on the drive gear. There are three conditions as we have briefly touched upon: direct drive, gear reduction, overdrive. We will study later on. A gear ratio is determined by dividing the number of teeth on the driven gear output by the number of teeth on the driving gear input. Number of teeth on the driven gear, let's suppose there are 24, and number of teeth on the driving gear is 12. So the ratio is 2:1. So it is a gear reduction. Now, there are 12 teeth on the driving gear, this one, and 24 teeth on the driven gear. So gear ratio is determined by dividing the number of teeth of the driven gear output gear 24 by the number of teeth on the driving input gear 12 teeth. So the ratio will illustrate 2:1. Here the drive gear having a 8 teeth and the driven gear having a 24 teeth. So the gear combination provides a gear ratio of 3:1. 24 divided by 8. So it is 3:1. So it is also a gear reduction. Now let's see one by one the three which we have talked about, the direct drive. If two meshed gears are of the same size and have the same number of teeth, they will turn at the same speed. So their dia is the same, the number of teeth is the same. So they will rotate in a same speed. Since the drive gear turns once for each revolution of the driven gear, the ratio is 1:1. This is called a direct drive. When a transmission is in direct drive, the engine and transmission turns at the same speed. So if engine is rotating at 1,000, crankshaft is rotating at 1,000 RPM, so transmission output shaft is also rotating at 1,000 RPM. Okay, so this is direct drive. So remember this condition. The two meshed gear of the same size and have the same number of teeth. So dia is the same and the number of teeth is the same. They will turn at the same speed. Then we call it as a direct drive. Now, the second case, the gear reduction. The same previous figure. If one gear drives a second gear that has 3 times the number of teeth, the smaller drive gear must travel 3 complete revolutions in order to drive a larger gear through one rotation. So this smaller drive gear have to make a 3 rotation to cover this one rotation. So divide the number of teeth on the driven gear by the number of teeth on the drive gear and we get 3:1 gear ratio. This type of gear arrangement where the driven gear speed is slower than the drive gear speed provides gear reduction, and that will be the ratio of 3:1. Now, the third case in which we have overdrive. Now we have a drive gear with having a 24 teeth and the driven gear is having a 8 teeth. Overdrive is the opposite of a gear reduction condition and occurs when a driven gear turns faster than its drive gear. For the gears shown in this figure, the driven gear turns 3 times for each turn of a drive gear. So the driven gear is said to be overdrive the drive gear. For this example, the gear ratio is 0.33:1. The overdrive ratios of 0.65:1 and 0.70:1 are typical of those used in automotive application. So overdrive is normally in 5th gear when engine speed is less, but the vehicle speed is more, the transmission speed is more. Let's suppose for journal, if engine is rotating at speed of 1,000 RPM, your transmission will be moving with more speed with the gear ratio if it is in this ratio. Now, another gear, idler gear. Let's see the figure. We have this drive gear on our right side. Then we have an intermediate gear, which is we call it as a floating gear or idler gear. Then we have a driven gear. Idler gears affects the direction of rotation in a gear train, but not the final drive ratio. Remember this thing. It's changed the direction, but not the final drive ratio. A gear that operates between the drive and the driven gear is called a floating gear or idler gear. So this is a floating gear or idler gear, which is operating in between the drive and the driven gear. Idler gears do not affect the speed relationship between the drive and the driven gear, so it do not affect the speed relationship, although they do affect the direction of rotation. Their main purpose is the primary purpose is to change the direction of the rotation. Reverse gears on a manual transmission often uses an idler gear to change the direction of a rotation. Now, the torque factor. Gear applies torque in the same way a wrench applies torque. The force applied multiplied by the distance from the center of the gear equals the torque. Let's suppose we are applying a 10-pound force at this very point, and the distance from this very point to the center is 2 feet. So the torque will be 20 pound-feet. Now, transmission construction. Speed gears, three major components: input shaft, counter shaft, output shaft, and gears with synchronizers. So all gears, first is the input shaft. Input shaft is the shaft which is attached with your clutch. From that flywheel, the power is coming to the clutch, and from that clutch, the power is coming to the input shaft. And from that input shaft, the power is transmitted to the counter shaft. And from that counter shaft, it goes to the output shaft or the main shaft, from where we select the gears and then we achieve the output at the transmission end. Okay. So all gears on the counter shafts are permanently attached to the shaft. So they are permanently attached to the shaft. They are not on floating or something like that. When the counter shaft rotates, all gears on the counter shaft rotates. So when there is an input shaft is rotating and it is driving the counter shaft, so all the gears which are permanently attached on the counter shaft, so they also rotates. The input shaft gear is also part of the input shaft. That gear which is on the input shaft is also part of the input shaft. However, the gears on the output shaft, the main shaft, are free to move on the shaft and are connected to the main shaft through the synchronizer hub when a shift is made. On input gear on the input shaft is a part of the input shaft, and the gears on the counter shaft are the part of the counter shaft, and they are permanently attached. But the gear on the output shaft, the main shaft, are free to move on the shaft and are connected to the main shaft through the synchronizer hub when the shift is made. The gears that rotates on the main shaft are called speed gears. The gears that rotates on the main shaft are called speed gears and are free to rotate on a film of oil or on bearings. So there is a lubrication oil is there, or they are rotating on a bearing. Now, the synchronizer parts and operation. Synchronizers are used in manual transmission oblique transaxles to make shifting easier. How they make easier? Let's see. When the driver depresses the clutch pedal, the torque is no longer being transmitted to the input shaft, and the drive wheels are driving the main shaft of the transmission oblique transaxle. So when we depress the clutch pedal, so torque is disengaged. So no transmission from the flywheel clutch to the input shaft. To achieve a clash-free, no grounding sound shift, the two gears to be meshed must be rotating at the same speed. So to achieve a clash-free, no grinding sound shift, the two gears which are to be meshed, they should be rotating at a same speed. The dents and the interlock hold the shift mechanism in position. We will see this in the next figure. The real shifting in a synchro mesh transmission take place in the synchronizer assembly, not the gear. So the real shifting in a synchro mesh transmission take place in the synchronizer assemblies, not the gear. Remember this thing. Most synchronizer assemblies rides on the output shaft between the two gears. We will see in the figure. A synchronizer assembly is named for the gears on the either side of it, which are the two speeds that it engages. For example, a 5-speed transmission with a constant mesh reverse uses 1 to 2 synchronizer, 3 to 4 synchronizer, and 5 reverse synchronizer. Let's see, this is your gear shifting lever. You have a ball socket arrangement, and this is your shift fork shaft of different gear. This is the shift fork. These are the springs and dents balls which moves this shift fork and engages it. A typical shift mechanism showing the shift dent designed to not only give the driver a solid feel when shifting, but also to prevent two gears from being selected at the same time. The shifter also prevents shifting into reverse except from the neutral position. So when the driver moves this shift lever, the gear shift lever, it basically moving the shift fork shaft, and that shift fork shaft is moving that shift fork, and that shift fork is basically moving the synchronizer sleeve. We will see. This is the synchronizer. Basically that shift fork, this shift fork is moving this synchronizer sleeve right or left. Now, let's see the synchronizer construction. This is your synchronizer sleeve. This is the stop ring. These teeth are called the clutch gear teeth, and this is your speed gear, or which is on the main shaft or the output shaft. The shifter fork fits into the grooves of the synchronizer sleeve. This shift fork is fit into the grooves of the synchronizer sleeve here. When a shift is made, means we have to change the gear. The sleeve is moved towards the speed gear. Then the sleeve is moved towards the speed gear. The sleeve presses the stop ring, synchronizer ring against the cone area of the speed gear. Then this sleeve, it has internal teeth here. So the internal teeth moves this stop ring and engages with clutch gear teeth here. The sleeve presses the stop ring's synchronizer ring against the cone area of the speed gear. This is the cone area of the speed gear. The friction between the stop ring and the speed gear causes the speed of the two becomes equal. So this ring and this clutch gear, this friction between the stop ring and the speed gear causes the speed of the two to becomes equal, permitting the sleeve to engage the gear clutch teeth of the speed gear. When this engagement occurs, the shift is completed. So this is how your synchronizer sleeve moves on the stop ring. It touches the clutch gear teeth and then they are engaged. So this is the synchronizer sleeve where the shift fork is moving this. This is your stop ring and this is your gear clutch teeth and this is your speed gear. Now, synchronizer keys are attached to the clutch hub. First, let's see. This is your ring grooves. These are the ring grooves and these are the keys. Here we put the spring keys, synchronizer ring. Then we have synchronizer sleeve. Then these are the key springs. And then we have this keys, clutch hub, then synchronizer ring, and then the clutch, gear clutch, and then the speed gear. Synchronizer keys are attached to the clutch hub. This one, here, here, and here, and push against the synchronizer ring, here or here, both directions. These grooves prevents lubricating oil from becoming trapped between the rings and the cone surface of the speed gear. The grooves also helps the ring releases from the cone surface when its shift is made out of the gear. Synchronizer construction, few words about this. Splines attached to the center hub of the synchronizer to the output shaft, so the hub and the output shaft rotates together. There are also splines machined on the outer circumference of the hub. So these are the hub splines are here. These are the external splines and these are the internal splines. So this sleeve moves freely on these splines. An outer sliding sleeve rides on the external hub splines with enough clearance so that it slides freely. The splines on the sleeves also matches the small coupling teeth of the stop ring and the speed gear. Here and here. Okay. Coupling teeth are also called engagements or clutch teeth. The coupling teeth are also called the engagement or clutch teeth. So these are the coupling teeth, which are called the engagement or clutch teeth. The sleeve is splined to the hub, so it rotates with the output shaft. The spline here it moves like this. The sleeve is splined to the hub. This portion here comes here and then here. The sleeve is splined to the hub, so it rotates with the output shaft. A stop ring sits between the speed gear and the sleeve. The coupling teeth on the stop rings matches those on both the sleeve and the speed gear. The stop ring also has a trapped tapered cone to match the cone machine on the speed gear. These are the tapered cones, okay? Small spring-loaded dent keys, also called synchronizer keys or studs, rides in the slot on the outer sleeves. The stop ring has slots to match these keys. This allows the stop rings to rotate slightly relative to the sleeve before the keys hits the slides of their slots and stop the stop rings. As the sleeves moves, the synchronizer keys moves with it, which pushes the blocking ring onto the tapered cone of the speed gear. Let's see by this figure. A shift sequence starts when the shift fork is moved by the driver. So shift fork is moving this sleeve, this one. First, applying a force on the sleeve that moves it towards the speed gear. So we applied a shift fork lever here and it is moving in this direction. The applying a force on the sleeve that moves it towards the speed gear. The sleeve and the insert contacts the stop ring, blocking ring, the stop ring and the gear cone here. So they are in touch here. The synchronizer ring, the stop ring, engages the cone on the speed gear, causing both assemblies to reach the same speed. So they are engaged here. Stop rings is pushed into the gear cone. So they are engaged and they starts moving in a same speed. The shift is completed when the internal teeth of the sleeve mesh with the gear clutch teeth of the speed gear. So when it is in full engagement, both the internal teeth of the sleeve mesh with the gear clutch teeth, it is fully engaged. So the power is transmitted to this gear. Now the transmission box or the working or the gearbox working. First see the neutral gear. The input shaft drives the counter shaft. All of the gears on the main shaft rotates. Main shaft, this is your input shaft up till here. Then this is your counter shaft and then this is your main shaft or output shaft. So input shaft drives the counter shaft. So this power is coming from the engine, flywheel and clutch to this input shaft and this input shaft is rotating this counter shaft. All of the gears on the main shaft rotates. All gears are rotating here, but no one is in contact. Okay. The synchronizer are not engaged with any gear and no power is transferred to the output shaft. So it is only rotating here and no power is transmitting from to the output shaft. In neutral, the input shaft and the counter shaft are rotating. If the clutch is engaged, clutch pedal up, but no torque is being transmitted to the transmission. So now we have the applied a first gear. So the power is coming from, let's read first. The power enters the transmission through the input shaft. The first oblique second synchronizer sleeve is engaged with the first gear dog teeth. Now this is your input shaft and this is your input gear, which is meshed with the counter shaft, and this is your first gear on the counter shaft, first gear on the main shaft, and this is your synchronizer, which this is your synchronizer sleeve, and your move have to the first gear. So it is in contact. So they are moving, and then we will get the power from this output. The power enters the transmission through the input shaft. The first oblique second synchronizer sleeve is engaged with the first gear dog teeth. The power is transferred from the input shaft through the counter shaft and up to the first gear. Input shaft, input gear, counter shaft, first gear, synchronizer sleeve attached, and power out. The first gear drives the output shaft. So it drives the output shaft and you get the power output. In first gear, the first and second synchronizer sleeve is moved rearward in this direction, locking the first speed gear to the output shaft. So it's locked the first output gear to the main shaft. Torque is transmitted from the input shaft to the counter shaft and then to the output shaft. So this is how the first gear is engaged. In second gear, this synchronizer assembly in first case, it is moving in this direction. Now it is moving in this direction and engaging this second gear with the main output shaft. The power enters the transmission through the input shaft. The first and second synchronizer sleeve is engaged with the second gear dog teeth. The power is transferred from the input shaft through the counter shaft and up to the second gear. The second gear drives the output shaft. In second gear, the first and second synchronizer, this one, sleeve is moved forward, which locks the second speed gear to the output shaft. So the power is coming from your engine, flywheel, and clutch to this input shaft to the input gear, which is driving your counter shaft. From that counter shaft, it is going to the second gear because we have moved this synchronizer to the second gear, and this second gear is attached then to the main shaft, and the torque is moving from this output shaft. In third gear, the power enters the transmission through the input shaft. The third and fourth synchronizer sleeve is engaged with the third gear dog teeth. The power is transferred from the input shaft through the counter shaft and up to the third gear. The third gear drives the output shaft. To achieve the third gear, the shaft linkage first centers in the first and second synchronizer sleeve and then moves to the third, fourth synchronizer sleeve rearward, locking the third speed gear to the output shaft. Now, previously we were engaging this synchronizer with first and second gear. Now, when we have to shift to the third gear, we will come to the neutral slot. Then we will move this synchronizer to the third gear in this direction, and third gear will be attached with your main shaft and the power is going outward. Now in fourth gear, the power enters the transmission through the input shaft. The third and fourth synchronizer sleeve is engaged with the fourth gear dog teeth. The power is transferred from the input shaft to the fourth gear. The fourth gear drives the output shaft. In fourth gear, the third fourth synchronizer sleeve is moved forward, which locks the fourth speed gear to the output shaft. In third speed, this synchronizer is moving towards this third gear. Now in here, this synchronizer sleeve is moving in this direction. So this direct drive is going on. So the ratio is 1:1. So power from the input shaft, fourth gear, which is attached with this gear, and power is going to the output shaft. Now, the fifth gear, the case of overdriven. The power enters the transmissions through the input shaft. The fifth gear synchronizer sleeve is engaged with the fifth gear dog teeth. The power is transferred from the input shaft through the counter shaft and up to the fifth gear. The fifth gear drives the output shaft in the overdrive. To achieve the fifth gear, the shift linkage first centers, then the third fourth synchronizer sleeve, and then moves to the fifth synchronizer sleeve towards the fifth gear, locking it to the output shaft. Now, power is coming from your input shaft to the input gear, then the counter shaft, from this counter shaft, from this fifth gear, and we have moved the synchronizer to the fifth gear and then going to the main output shaft. So you're achieving overdrive due to these gear ratios. Now the last one is the reverse drive. The power enters the transmissions through the input shaft. The reverse gear synchronizer sleeve is engaged with the reverse gear dog teeth. The power is transferred from the input shaft through the counter shaft through the reverse idler gear. So one gear, addition of one gear here, that is the reverse idler gear, and up to the reverse gear. The reverse gear drives the output shaft in the reverse direction. Actually, this idler gear or the floating gear is in between the counter shaft and this reverse gear. Just for your ease, it is actually not here. It is basically in between this counter shaft and this reverse gear on the main shaft, so that the direction should be changed. The torque flows through the transmission in the reverse gear. Note that this idler gear drives the 1 and 2 synchronizer sleeve gear, which is splined to the output shaft. So remember this thing. In modern transmission or the gearbox, we have a reverse gear with the synchronizer. But the previous version, which we were having, in reverse gear or in first gear, we do not have the synchronizers. So as you have seen, if you have to go to the move in the reverse direction, you have to completely stop the vehicle and then you have to apply the reverse gear. It is not like this, you're moving in the forward direction and then you suddenly apply the reverse gear. No, it is not like this. You have to stop the vehicle at almost to the dead stop, and then you have apply the reverse gear. In few transmissions, your first gear is constant mesh or sliding mesh, and reverse gear is also a sliding mesh type. So this comes to the ends of this, our second lecture of this automotive technology course. A few video clips I will upload separately because in the last lecture there was some voice problem, so I will upload separately for your better understanding. I hope you like my videos. Kindly do share. Thank you very much.